the product of it.
Hi everyone, welcome back to the second talk of the day. We're very excited to have Simran here. She's a PhD student at Stanford working with Chris Ray. She works at the intersection of machine learning and systems and thinks about understanding the quality efficiency trade-off to make computing faster for these large language models. And you might have heard of some of her works like Monarch Mixer, Zoology, and so on. She recently gave a great tutorial at Stock as well, and she's on the faculty market. So we're very excited to hear from her. Thank you.
Hi everyone, I'm Simran. I'm excited to be here today to talk about my research at the intersection of ML and systems. So we've seen a lot of promising results in this area, especially recently, that I'd love to share with you. Nowadays we have amazing ML models that can do things we didn't think were possible a few years ago, whether debugging code, generating fun photos, or predicting protein and RNA structures. We'll try to understand what enabled these advances, what are some of the outstanding problems, and how can we tackle them. So one popular narrative is that data and model scale has improved model quality and given these models new capabilities. We can scale in parameters, we can scale in sequence length or context length, we can scale in the number of samples that we generate, shifting to a sort of, generate many samples and verify and find the correct one out of these samples kind of paradigm. While the progress is astounding, our core primitives are inefficient, limiting the potential. So a key bottleneck in ML right now is compute. The transformer architecture, as we know, which powers all the industry models, requires compute and memory to grow with the input size, precluding dreams of, say, modeling the 3.2 billion nucleotides in human genome sequences or repositories containing millions of lines of code. Concretely, attention scales quadratically in the input sequence length during training or the forward pass during inference, and linearly in the compute and memory during decode steps during inference. The MLP scales quadratically in the model dimension. And the scaling gets even worse if we want to support things like chain of thought or tasks that are outside the complexity class of just basic parallel transformer execution. So over the past 2 years, in the wake of rapid model scaling, there's been a Cambrian explosion of new efficient architectures that rival transformers, always accompanied by some sort of Dolly mascot. And excitingly, these works often, say that there's outperforming transformers. And so maybe this is a solved problem. This is, from the announcement of Mamba, which was super exciting and made a ton of progress. So taken all together, the picture right now is there's a class of efficient model architectures that are far faster and cheaper to run than transformers, and importantly, seem to generate text that's just as high quality. Yet despite these promising results, all the organizations are sticking with transformer models. And it makes a lot of sense. If we don't know the price of the meal, then why should we start training these efficient models? We really need more work to sort of unpack the trade-offs. The saying goes in ML, there's no free lunch. So let me briefly outline the rest of this talk. First, I'll give a quick recap of the main efficient language modeling classes, just so we're on the same page. What are the prevailing approaches? Then I'll go through a detailed error analysis of these different models at a pretty broad scale and see that indeed there is a remaining quality gap. Then we'll use theory and synthetics to reason about why these gaps exist and motivate ideas to close the gaps. And then we will scale these up. And as a foreshadowing, we are putting out sort of a first linearized 405B model in the next ICLR sprint, so it's exciting. So I'll tell a story today about this research question, and just a few motivating pieces to keep in mind as we go through the talk are, there are many different ways to think about efficiency. Let's see what the frameworks are and how they relate. We will think about the frameworks that we can use to understand the quality differences between architectures. And then we will think about the tools that we can use to build new efficient architectures on an academic budget. All right, so starting off. Just to make sure we're on the same page, problem with attention is that, again, GPU memory consumption grows linearly with the sequence length when generating. And this really tanks our throughput. So during inference, we typically retain all the key and value representations in what's called a KV cache. So this grows with the size of the input. The alternatives are much faster because we're trying to have scaling that's using a constant amount of memory regardless of the sequence length. And there are two main categories of efficient architectures that people are excited about in this space right now. So one is linear attention and the other is state-space models. So let's just quickly recap. Linear attention. The main idea is to take the queries, keys, and values just as for standard attention, but rather than compute softmax of qk transpose, we're going to replace the exponential with some feature map function phi of q, and then we'll have phi of k transpose. What this permits is that we can now reorder we can change up the order of our matrix multiplies to get linear scaling in sequence length if we multiply keys and values first. During inference, again, if we multiply keys and values first, the resulting what's called kv state ends up having dimension roughly d squared. And regardless of the number of tokens that we see, we're just updating this constant kv state, constant sized kv state that's independent of the sequence length. So for linear attention, we have constant memory versus this memory growing with sequence length. So this is the picture right now. When we care about training complexity, inference complexity, and whether our training is parallelizable. Now state-space models. I'll go through these briefly. Also, recursive form, but instead of having queries, keys, and values that are defined as projections of our input tokens, x sub t at time step t, we have these fixed matrices, A, B, and C, that are learned and trained during training, and then they're fixed during inference. So what this means is if we unroll the recurrence for multiple steps and think about what it looks like at step n, because A, B, and C are fixed, we can actually rewrite it as a convolution operation with filter function k defined in terms of these A, B, and C matrices. This filter function is same size as the original sequence length, so n. And the resulting sequence mixing matrix, so how different tokens in this n long input that we're providing to the model get to interact, follows this sort of Toeplitz sequence matrix, sequence mixing structure. And because of this structure, we can apply fast algorithms like the FFT to compute with subquadratic scaling in sequence length. All right, so just to recap this intro section background, our resulting sequence mixing matrices, we have linear attention and then these convolution SSMs. Great, so we have exciting, efficient architecture classes that scale much better than attention. But what are the quality gaps, if any? This is a very broad question, so language modeling is very complicated with many different subskills and subtasks. So correspondingly, we took a pretty broad approach. We just trained on very standard training data and infrastructure a bunch of different efficient language modeling candidates. It's the very, very first step. And there were clear quality gaps in perplexity, but what does this mean in terms of why these gaps exist? So given this broad starting point, we took a very broad approach of just doing manual error analysis, one by one through many, many different inputs, next token predictions. Again, there are many different subskills in language modeling at many different levels of abstraction, so it's not clear that we would find anything interesting. But surprisingly, a single scale associative recall was the glaring failure mode for efficient language models. So just to walk through a quick example here of a test sequence from the PILE language modeling dataset, if we have Pixar Fest as a bigram or pair of two tokens coming earlier in the sequence, the second time around we can see that both attention and our efficient language model get it incorrect, depicted in red, but the second time attention is able to predict out Fest, referring back to the original bigram. And this is a very one-off example, but how does this observation scale up? So we put together proxy metric to scale this up to the entire tens of billions of tokens in the data set. What we did was basically say, yeah, anytime there is this repeated bigram, let's focus on the second occurrence of the completion. So like the second version, instance of buzzard, and call that an associative recall hit. Furthermore, many tokens, or many bigrams, like maybe UC Berkeley, appear many, many times in the training data, and so that might be something the model just memorized. So we further stratified based off of the number of occurrences in the training data. And when we did this, the gap between attention and the efficient model candidates, such as Hyena and RWKV, became hugely apparent when we looked at perplexity. In summary, associative recall accounted for 80% plus of the gap between transformers and the efficient language modeling candidates on average, despite representing just 6% of the tokens. What gives? This was very surprising given all the discourse around these models as matching transformers everywhere. And to study, and all these prior works actually indeed studied associative recall and showed that their models could solve associative recall. So these are snapshot results from tables from different ones of these papers. So this was even more surprising to us. And we looked at perplexity, but what about real tasks that might require recall? So let's think of document QA, where you've seen a long document, you need to answer something. Or you have a list of lemmas, you need to generate the next line of a proof. Or you have code generation tasks and need to remember function names, variable names, information extraction. So we took a set of these tasks and evaluated a bunch of these models and found that indeed, while these models could match on non-recall tasks, things like classification, there were pretty massive gaps when we looked at recall tasks. So let's go through why these gaps might occur and the explanations that we put together. Are there any questions so far? Yeah.
Thank you so much. This is super cool. Do you think the associative recall task is related to the induction head task, or are they completely different?
Yes. Yeah. So yeah, there's a bunch of prior work here, and you can read our paper for a strong related work section and all of these. So we'll consider each of the architecture classes that we looked at and how they might solve associative recall. So what does it take to solve associative recall? First, we need to compare which pair of tokens in our input sequences match. So maybe C matches back to the prior C. And then we need to shift forward the corresponding value that C maps to. For instance, C maps to 8 or A maps to 3. Attention makes it very easy to find the locations of matching keys in the sequence, since it takes all n-squared inner products between tokens. So we can easily identify the locations in the sequence of matches and then use positional encodings to shift these forward. But our gated convolution models, or SSM models, mix in much more restricted ways. We have this Toeplitz, or diagonal constant, sequence mixing matrix. So a token can look back m positions in the sequence only if every single token also looks back m positions in the sequence. This is very restrictive because in general language, we might need to do these interactions at arbitrary positions. Luckily, for these models, we're actually applying a unique 1D convolution to every one of the d dimensions in our n by d input. So we can support multiple shift distances. But for the O of n squared different interactions that we might need, we do need to support all of these different shifts and dimensionality. We would effectively need to store full representation of the sequence in one hidden representation in order to be able to support these matches. Or the dimensionality would need to grow in the sequence length to store a full copy of the input in a single embedding. Of course, this is just an intuitive explanation. We'll get into making this a bit more rigorous in a bit. So why were the older associative recall tests insufficient? And what can we learn from this experience? Well, when we take a look at them, a lot of those tasks were considering 1,000 long sequences with something like a vocab of 50 tokens. And so this means that every single one of these key value mappings, like C maps to 8 and A maps to 3 that I mentioned, can occur many, many different times in that 1,000 long sequence. So even with a small number of convolution shifts, that could be sufficient to identify the right mapping and output the answer with 100% accuracy. So we put together an improved synthetic called MQAR, where made the vocabulary size similar to real language modeling, where vocab is generally much larger than the model dimension. And wanted to see whether this better captured the trends we were seeing on real language modeling. So we measured quality on MQAR as a function of model dimension, shown on the x-axis here, and then sequence length, shown across the different 4 plots. So sequence length 64 through sequence length 512, across a variety of gated convolution and attention architectures. Per our intuition, attention requires only a constant model dimension to solve MQAR, regardless of the sequence length here. But gated convolutions require scaling the model parameters with the sequence length. All right, but there are many variants of these SSM architectures now coming up every week, and they have a lot of different subtle variants. So maybe some of those fix the issues that we've described. We turn to sort of a more theoretical lens to reason about this messy landscape in a more systematic way. So the main observation, simple observation, is that each of the operations in our popular efficient models can be expressed as a polynomial operation. So the Hadamard product or gating involved in these gated convolution models, we have our 2 data-dependent vectors u and v, compute a Hadamard product between them, and at each output position we get a degree 2 polynomial. For the convolution, recall that one of the vectors is typically a fixed filter that's learned during inference, and we have one data-dependent vector, our input, so we end up with a degree 1 polynomial. For linear attention, we have these 3 input-dependent terms, again, a polynomial operation. So our work takes steps to unify this messy landscape by expressing the diverse models as arithmetic circuits. People in this room are probably familiar, but an arithmetic circuit is a directed acyclic graph that represents a polynomial function of the circuit's input variables. And we can express our efficient models as general arithmetic circuits with n by d input variables. Each node in the circuit is an addition or a multiplication gate in these arithmetic circuits, and each operation takes 2 inputs. So arithmetic circuits provide a natural and powerful computational model for studying the complexity of a polynomial, and the complexity of a polynomial is the size of the smallest arithmetic circuit that computes the polynomial. Right. So again, we have n by d input variables to our circuit and n by d output. So we looked at the landscape of efficient language models and distilled them down to a simplified architecture that we refer to as BaseConv. Yeah.
So you can only construct these arithmetic circuits at inference time.
Yeah.
So you have to train the model from then, actually.
Yes. Yeah.
Whereas the problem, the pre-training, right, the attention is quadratic.
Yeah, so
Because at inference time it's linear. Catch.
and what is the sort of
So,
question?
like, it doesn't solve the problem at pre-training, right?
Are you saying like it doesn't answer what actually gets learned by these models versus?
The quadratic dependence of transformer.
Okay, yeah.
You keep saying solve a problem. Can you be specific about what problem you think is being solved? That seems like might be the disconnect.
Yeah. Is it you're talking about inference or training?
I'm talking about whether we're going to study whether MQAR specifically, a circuit to solve it, can be represented in these models. and what kind of model dimension or number of model parameters or broader notion of scaling is required to represent that circuit.
When they're completely trained.
When they're completely trained, yes, yes. Correct. Yeah, so there are no, there's no theory here about like the actual optimization or learning procedure or gradient descent or anything.
No, you can actually, you can also talk about, I want to make sure that my model, at training time, I have an architecture that at training time
Sure. Yeah.
is linear.
Yes. So this is only at inference time. Yes. Yes, that's correct. So these are only for post-trained models. We have the coefficients on these polynomials, and then can write them down. Right. So we took this landscape of efficient language models and distilled them down to a simplified architecture that we refer to as BaseConv, and show that we didn't really lose anything with the simplification. So BaseConv here has a linear map on the right and a convolution in the inputs on the left with these bias terms. So for, we proved that BaseConv can simulate any general arithmetic circuit with only a polylogarithmic blowup in the number of parameters. For specific instantiations of these popular gated state space models like Hyena, we can even get rid of this polylog factor. So I want to highlight a couple of points to help contextualize this result. So first, arithmetic circuits take ND input variables and can do any arbitrary computation on them. But notice here that we have our linear map only operating on columns and our convolution only operating on rows. And despite this restriction, BaseConv doesn't really lose any power there. Arithmetic circuits, next point, arithmetic circuits are non-differentiable objects, but BaseConv is differentiable, and it can help us perhaps learn about, reason about how models actually learn. And then, BaseConv is hardware efficient, comprising just convolutions and multiplications. And this result built off of, prior work on monarch matrices and kaleidoscope matrices and so on, that focused on whether we could simulate linear arithmetic circuits and kind of generalized it to general arithmetic circuits. So BaseConv is nice because we can take this messy zoo of models here and reason about them using this BaseConv tool. So yeah, due to this equivalency between general arithmetic circuits and BaseConv, we can pick sort of an optimal circuit to represent our new gated convolution model here, and then claim that it can be simulated with BaseConv. Why might this be useful? So if we can write down a circuit that solves MQAR, then we can use the equivalency property to get sort of an upper bound on how large our models need to be to solve MQAR as a very first step. A naive algorithm would use, say, a sequential pass over the MQAR input sequence and hash the keys and values, log in insertion, and then do the lookup on the MQAR queries. We also came up with, in the paper, with a more efficient parallel circuit by invoking the parallel binary search algorithm. But if we have this powerful BaseConv tool, why not just do everything with this? It's easy to reason about. But the issue is that there's this polylog factor on the depth in our bound. While polylog might be relatively tight in theory, we pay a lot in actual model training if depth is too large. It makes things unstable and hard to optimize. We really want to know if we can solve MQAR in constant many layers like we can do for attention. So can we do better? We prove a lower bound on the number of layers of BaseConv required, showing the dependence on the sequence length. So the main conceptual takeaway here is that when we talk about these convolution SSM models, we're saying, okay, we can do subquadratic processing of an input in sequence length, but they appear less efficient at actually learning a critical task that we care about for language modeling, being associative recall. So we look for something else. Maybe linear attention, which actually has this input-dependent sequence mixing property. Just to recap linear attention, we saw it at the beginning of the presentation. we're going to replace the softmax of qk transpose with some feature map function phi of q and phi of k transpose. And here, it's very clear that these models have pretty different working memories during inference. And so we show, using simple, invoking the index problem and communication complexity, prior results, that any recurrent model depending causally on input u requires omega of n bits in state size to solve MQAR. So there's this fundamental trade-off here between, quality on associative recall and memory. Going back to our synthetic, just to depict the picture, attention achieves perfect recall but has a huge recurrent state due to the KV cache. A very simple input-dependent sequence mixer that's still subquadratic is sliding window attention. And that does reduce the memory consumption, but at a drastic cost to recall. And gated convolutions fall even below sliding window attention. So here's the H3 and hyena architectures. So can we expand the Pareto-frontier? Following polynomial theme, we'll take a very simple idea of let's just let our feature map function phi be a Taylor approximation of the softmax exponential function. So recall we have like 1 plus x squared over 2 factorial and so on. Applying these to our queries and keys, it looks something like this. We have 1, q outer product with q, and then the scaling. And when we multiply these together pointwise, we recover Taylor approximation of what should be clear here is that as we increase the number of terms in our approximation, the fidelity with respect to approximating softmax increases, but the size of these resulting 5q and 5k output tensors also grows very drastically. So because we can't just use infinite terms, obviously, we're going to restrict to something like a 2-degree polynomial for their approximation. So it's not perfect attention, but we'll combine with a dense sliding window attention just of width something like 64, which is very nice for the hardware, and then combine these to get a simple model that we called based. We can take a look at how this compares and see that based expands the Pareto-frontier on this memory and recall trade-off space. And the yellow here is the Mamba architecture. But again, there's this fundamental memory bottleneck, and one teaser idea that we explored, I'll only briefly state it, is what if we can just let the model make multiple passes over the data? Very basic idea in theory and extensively studied, but right now there's a lot of focus on these causal language models, and everyone is trying to get these efficient models to sort of exactly just have the same experience when we use them as transformers. But if we just let the model take multiple passes over the data, then maybe after seeing the document in question once, the model can condition on that to be more effective in deciding what to store in its second pass, given a limited amount of memory. So called this idea, just read twice, and this is just a small part of the study there. And so with these results, we can close much of the gap to transformers over Mamba, and also with just read twice, kind of be competitive with the transformer model after all of this effort on these associative recall tasks, at least the ones that we studied. Okay, so we've made progress in sort of understanding what the important ingredients are for our efficient architectures and the fundamental trade-offs that we have here. But how can we scale these up and do these ideas transfer to the 7+ billion parameter skills that people care about? It has been challenging to take ideas that are efficient in theory and to achieve wall clock speedups. So for instance, linear attention has long been far slower than well-optimized attention or flash attention. So we have these nice theoretical models of efficiency, but it's not clear whether we can implement our architectures with all the hardware constraints to compete with attention. And one thing I didn't really mention here is like, okay, what are the relative state sizes of something like Mamba and Base? And indeed, like that does account for most of the quality improvement here, is just that Base has an 8 times larger recurrent state size than Mamba. But what does that actually mean from a hardware efficiency perspective? Does that mean, you know, Base is slower, or are there real wins along this Pareto-frontier? So the last piece I wanted to talk about was, you know, hardware efficiency. So the GPU has a memory hierarchy with small, limited amounts of fast memory. So registers are the fastest memory. More of shared memory, so different threads can communicate over shared memory in the same warp, and then a lot of DRAM. So if we think of like our NVIDIA H100, 80 gigabytes, there's 80 gigabytes of the DRAM. And when I mentioned that, you know, making these architectures efficient is hard, it's even hard for the thing that's the most widely used in industry, which is attention. Flash Attention 2 suffered a 47% performance degradation going from the A100 to the H100. And it took over 2 years since the release of the H100 to develop Flash Attention 3. I mean, these were all written by my friend and lab mate, but still, alas. And so, let alone exotic emerging architectures like Mamba. And beyond just, you know, writing high-performance AI kernels is difficult, it's also hard to understand which architectural operations map well to the hardware. So Mamba's design prevents it from using the tensor cores, which are just the fastest compute available on the GPU. 16 times faster on the H100 than the general compute for things like the X, for the things handled by the ALU or the XU units. So we put together, in some of my recent work now, a programming library for CUDA. So you can think of it like, the spirit we're going for is sort of PyTorch-like experience for CUDA. There are a couple different systems design fundamentals here. So one is everything is in terms of a 16 by 16 matrix tile basic data structure. So rather than thinking about unit by unit flop operations, we want people to think in terms of these 16 by 16 units. We also provide a series of familiar PyTorch or NumPy-like primitive operations. So what you can see here is attention written in PyTorch with line-by-line CUDA code in ThunderKittens. And for context, something like Flash Attention 2 is 1,200 lines of CUDA. And so it's hopefully making CUDA slightly more accessible. And then the next idea is we want to understand what are useful general patterns about writing CUDA that can simplify the process for new users. Can we take care of some of these general programming patterns and put them into the framework and allow people just to fill in this template in order to get high performance kernels? So we start to explore this broad question. We have simple cost models in terms of there are many different execution pipelines on a GPU. So there's ALUs, there's XUs, there's these all handle. We've kind of shown the different execution units that handle different operations in attention alone there. And you can think of, we have some number of flops per compute pipeline that we need to handle. We have some number of bytes transferred at different parts of this memory hierarchy, so at different memory bandwidths. And we have variable numbers of parallel workers that we can instantiate our kernel with, which modulates what's called the occupancy. And so the worst case is if everything occurs sequentially on these pipelines. The idealized case is we can strongly just overlap everything. But of course, this is an ideal case. And there are real fundamental trade-offs here when it comes to writing high-performance kernels that we start to identify when we put together a project like this. So for one, if we increase the occupancy or have more workers that are executing our AI kernel, the basic GPU operation in parallel, then yes, we do see higher teraflops supported or higher efficiency from our kernels. But then there's a trade-off that starts to occur. if the occupancy is too high, workers need to start to contend on limited hardware resources. For instance, the limited fast registers that I mentioned at the beginning. So why I mentioned this to this audience is that it would be very exciting if we could have richer cost models for these architectures and frameworks to help us take these efficient architectures that we're developing at a rapid pace and start to be able to make them high performance at a faster pace so that we can compete with transformers. So using TK, we've put together a broad set of concise and performant kernels for different AI workloads. And here's an example for the based architecture where with TK we can get much faster than a sort of comparable kernel written in Triton for the same architecture. And the reason for this is that TK is an embedded programming language, so it's in the lowest levels of CUDA and can take advantage of that low-level access, whereas a lot of things that are important for high performance are kind of abstracted away in Triton. All right, so that was the overview of the talk. And what's been really exciting in the most recent work is that we've combined all these ideas to build the first linearized 405 billion parameter model. And so a big issue in academic research around these architectures right now is that we have been pre-training at something like 1 billion, 2 billion parameters at the very largest versions of these projects. So there's been a ton of work on recent work, maybe 3 or 4 different works that are taking pre-trained transformer models, say like Llama 8 billion, and converting them into linear versions. So what's typically done is you'll initialize your model with the weights from the pre-trained transformer model and then do some sort of distillation process to make it linear. It's been really hard to do this actually, so some of the existing methods are all bottomed out at like 8 billion parameters and still take hundreds of billions of tokens and actually drop quality on MMLU quite a bit. And so we've been excited to see some of these results. These are still early, going out for ICLR, but just to highlight them here in our very V1 conservative numbers, we're able to sort of close a lot of the gaps on LM eval harness across all these skills, do this all on an academic budget with just 4% of the tokens there. All right, so returning to the motivating questions at the start of this talk, there are many different ways to think about efficiency. There's the motivation often mentioned is that, okay, these primitives are subquadratic as opposed to quadratic attention. But that might not matter as much as thinking about the efficiency for solving tasks we actually care about in language modeling. For instance, recall. We've also talked about efficiency in terms of the number of arithmetic operations required and hardware efficiency. In terms of what frameworks we can use to reason about the quality differences, we showed sort of the unreasonable power of synthetics here, and when we have a really precise formalized problem that actually ties to something that manifests in the real data, then we can start to make progress in theoretically analyzing that problem. But it's hard to get the synthetics right, and so it's really important to have both that back and forth between the downstream experiments and synthetics. And then we also showed off this BaseConv tool. We've recently been using BaseConv to show that, I'll get to this at the end, but something about scientific computing tasks with these models is very exciting when it comes to BaseConv. And last bit here was what tools can we use to build new efficient architectures on an academic budget. So again, these synthetics are really useful. They allow for fast iteration of new architectural ideas. Things like CUDA libraries, things like linearizing and leveraging the large pre-trained transformer models that already exist. And we've been excited to see these ideas get used, and this is all due to an amazing team. Here are the papers that I discussed, and feel free to reach out to me with any questions.
So there are other ways actually to get linear time, right? So linear transformer is just one way, and actually theoretically, you can show that linear time with this particular architecture cannot guarantee any heterogeneous norm between the approximation of softmax and bottle radioactive. So that might be actually the main issue. Like,
Yeah, perhaps.
no, it is actually the issue, not perhaps. So you
Yeah.
can actually show that this is like, they are not guaranteeing the approximation based, and.
Yeah, I think the situation.
But there are other ways, and to do that, it's not like, I think going through polynomials might not be the right way.
And yeah, could you expand on that a little bit?
So
Why
there
do
are
you think
actually
it's not the right
people
way?
who try to approximate softmax.
Yes, that's correct, yes.
To sketch softmax exactly because of this, and they don't see this degradation.
Mm-hmm.
That is what I'm saying. Like, that is the issue that, you try to approximate softmax with, another operator that is known
Yeah.
not to be a good approximation is the issue. So, instead of doing that, sketch the softmax directly. And
No,
then you don't
that's
see
very
the-
fair. Yeah. So I think the goal of that part was less to say that this Taylor approximation is the best possible parameter, like featureization for this architecture or any linear architecture. I totally agree with that. It was mostly just meant to be sort of a natural side by side to the softmax, like maybe the first approximation we might think of. And the main point was about this memory and recall trade-off. So I agree with you. Yeah, there are many different ways to featureize these things. And not all of them are purely polynomial. So this is a polynomial approximation, but things like Mamba even do use like an exp in various parts of the architecture, and those things are not naturally handled by this framework.
So you mentioned that it took some years between between H100 and attention-free implementing something like flash attention. Now that it is well adopted, do you think that it will take so long after release of next GPU generation until flash attention 4 appears? Now that it seems like NVIDIA is prioritizing this, I assume.
I think for attention and for matrix multiplication, there's always a lot of effort. And so I think beyond flash attention, there are a bunch of other teams like Colfax and people who've been optimizing both attention and matrix multiply. So I agree with you that I think the gaps will definitely decrease over time. I think for these efficient architectures, it's hard to get a strong team to implement it for you. And so it's useful to have nice and simple tools like Triton or whatever other tools to support that.
You mentioned that the associative recall task was responsible for like 80% of the discrepancy between like the true attention and ordinary experience. Do you have any intuition for like where the other 20% is?
For some tasks, it was like 100% in some sense. Just take the perplexity gap and divide by the total gap. But for some models, I mean, there's obviously like how well you can memorize, and these models have very different MLP structures. So Mamba, for instance, does very well on memorization. It has a depth 48 architecture at a for fixed parameter scale, whereas like for the same parameter scale, a transformer would be something like 24 layers. And so the properties of the MLPs, which are believed to be responsible for memorization, are pretty different across these things. That's one explanation, but otherwise, there are other things that we can see in there.
You mentioned this process of like coming up with synthetics that are kind of tied to data, and it's back and forth. And I think this is a really nice example of coming up with like a synthetic that is like very grounded. Do you have any like advice or like best practices for how to do that?
I think so just to provide another example, I think maybe this helps answer the question. So we wanted to see if these models could solve least squares or scientific computing problems. And there's been a ton of work showing that transformers can, or linear attention can do gradient descent. And there's like this theoretical work from Jason and folks at Princeton. And then a jump to sort of, okay, if linear attention can do it, transformers can do it, and then you see least squares being done in context. But if you look at that result, the machine precision, the precision that the transformer gets is like something like 8, 9 orders of magnitude off of machine precision. And we've had numerical algorithms which can get to machine precision for many, many decades and years. And so once, I think to answer this question, it's like once we have this kind of empirical phenomenon that we've observed and this higher level idea, then let's start to tease apart into the smallest possible problem that we can. And so like an approach we took is that, okay, there are like affine maps, there are multiplies, there are reads, and these sort of primitive operations that are required in our numerical optimization algorithms like gradient descent or Newton's method or whatever it may be. And so like let's see how a transformer or gated convolution or a polynomial model or different things can represent those different primitive operations and see the first thing that breaks. And so maybe all the models get really good at reads, really by good I mean high precision, close to machine precision, but maybe transformers with softmax bottom out on the multiplies. And so I think the idea was, if we see some sort of big empirical gap, then try to like tease it into the smallest possible piece that we can find.
If there are no other questions, we'll thank Simran, and we can take the rest of the questions in the break. We'll be back at 11:35 for the next talk.